Welcome to the next video in a course in real analysis. We are talking here about the solutions to the exercises in the previous lesson. So here, recall what was the first exercise to show that the set of real 2 by 2 matrices are a group under addition. To do this, we must show that plus is an operation, that plus it is associative, that it has an identity, and that it has all inverses. So let's get started by confirming that plus is an operation. But that is very trivial because the definition of the sum of 2 by 2 matrices gives that the result is a 2 by 2 matrix. Next, let's check that this operation is associative. Now, to check that the operation is associative, we need to think about three matrices and how we could add them with various parenthesizations. And here's how I have chosen to display this calculation. So I am starting in the upper left with paren a plus b close paren plus c. And in the first equation on the top line to the right of that, you see that I am basically just spelling out what that means in terms of the coordinates of the matrix. So the upper left coordinate of matrix A was lowercase a. The upper left coordinate of matrix B was lowercase e. And since those are in parentheses, those get computed first, so we sum them together. Then after that is done, we think about the upper left coordinate of matrix C that was given by the variable I. And so that gets added next, and all of that makes up the upper left coordinate of the result. You can see that if you check back with the names of the coordinates of A, B, and C, and you go through all four coordinates, that this that I have displayed in the upper right-hand corner is the result. And what comes next is kind of the key step, which is that we now refer to the associativity of the real numbers, right? So all of these are supposed to be variables representing arbitrary real numbers, and we will, just the point of this exercise is just to work with the real numbers in intuitive ways, right? So like I haven't yet said what the axioms of the real numbers are, but we know that eventually we're going to have that the real numbers are associative under addition. And so that's how I'm shifting the parentheses inside the coordinates. That is basically a reference to the associativity of the addition for the real numbers. Okay, and then we kind of just export this all back to the language of whole matrices by saying, well, this is the same thing as A plus paren B plus C. You can sort of reason through that, right? So if you kind of notice the pattern at the very beginning in the upper left-hand corner with paren A plus B close paren plus C, that was writing things in the language of these entire matrices. And then we translated it all over to the coordinates of the matrices, worked with the coordinates of the matrices. We were allowed to make some moves there because of the things that we know about the individual elements, the real numbers. And then at the end, we kind of export it all back out to the language of whole matrices. And that shows that you're able to shift the parentheses around and this object stays equal the whole time. So that concludes the demonstration of associativity. Let's move on to completing the demonstration that this set and operation are a group. So now we need to talk about the identity element. Now it's very easy to check by a coordinate-wise sum that the matrix of all zeros is the identity element for 2 by 2 matrix addition. And I take it that that is clear and simple enough that I don't need to explain it any further. So let's now move on to talking about the inverses. And so if we have any matrix A, then if we take negative A, which we standardly understand to mean that you just multiply all of its coordinates by -1. That gets you the additive inverse. You can demonstrate that that is the additive inverse again by a coordinate-wise sum, which I take to be clear and simple enough that you can handle that on your own. And that concludes the demonstration that this is a group. So let's move on to the second exercise, showing that the set of all real 2 by 2 matrices under multiplication is not a group. And we can cut straight to the chase by noticing that the identity element for matrix multiplication in the 2 by 2 case is the 2 by 2 matrix of ones along the diagonal, zeros everywhere else. That's our identity element, the identity matrix. But somewhat famously from linear algebra, we know that certain matrices do not have a multiplicative inverse, an inverse matrix as we often call it in linear algebra. And just for the sake of variety, I've named two such matrices. The all zero matrix and also the all one matrix are two examples. There are many more. But let's now move on to exercise number 3, showing that if we take the set of matrices 2 by 2 real that are invertible, we will show that this is in fact a group. Now let's think, is the set non-empty? Yes, there are 2 by 2 invertible matrices. Is the function of matrix multiplication an operation? Yes, if you multiply two 2 by 2 matrices, the result is a 2 by 2 matrix, still with all real coordinates. And is the product an invertible matrix? Yes, right? So famously from linear algebra, the product of any two invertible matrices is an invertible matrix. So the multiplication function is an operation. We have already said that the identity element is the identity for this operation. And all that remains is for us to check that every element has an inverse, but precisely because we restricted to the invertible matrices, then each such 2 by 2 real matrix has a matrix inverse, and that will again be a 2 by 2 matrix. So yes, indeed, this has all of its inverses, right? Every element has an inverse in the set. And that concludes the check that this is, in fact, an example of a. So let's now move on to exercise number 4, where we have this abstract set and operation. We will show that this is a group, so is the set non-empty? Yes, obviously. Is this function an operation? Well, every element in the Cartesian product is represented by inputs, and it only outputs elements in X. So yes, it is an operation. Next, is it an associative operation? Well, as I described in the previous video, we're going to check this by looking at every possible triple and inserting parentheses in various places. So let's start with this first line where I have A star paren A star A, and we need to compute that. Now, the parentheses tell us that we have to start by computing the paren A star A. The parens indicate that order must come first. And when you look in the list of all the equations, you see that A star A computes to A. And so therefore, the result is A star A, right? So the leftmost A is simply carrying over from the previous A. The rightmost A is the result of that calculation. But now that this has turned into A star A, we again look up that calculation in the list of equations, and we see that that results in simply A, using the same fact all over again. But now let's look at the right-hand side of this equation, which is paren A star A close paren star A. And now we have to compute this as well. But if you think about what the left-hand side, the stuff inside the parens, must compute to, we know that that turns into A. And that is the same as a value that we found right here. And then, yet again, just like it happened the first time, this then turns into little a, so we now know that all of these are all equal to each other. And so that is the confirmation for when everything is a, right? A. Now let's move on to the confirmation when we have AAB. That's on the second line. So again, we're going to start first with the stuff inside the parentheses, this time meaning that we compute A star B. We need to look up what that is in the list of equations. And we see that A star B computes to B, as you see here. And now we compute this result, so A star B again turns into B, which you see here. And yet again, we have to then look at the far right-hand side where the parentheses are in the remaining other position and start computing this. So that means we need to compute A star A. Now, A star A turns into A, which again delivers something that we've already resulted in before. So let's just indicate over here that what we're getting is A star B. And again, that turns into B, which is the same result as what we got when we computed the first parenthesization, and so they come out equal again. Now, the explanation for line number 3 is almost identical to the explanations for lines 1 and 2, so I won't go through it. Notice that the fourth line is a little bit different, and so let's just talk that one through a bit. So we know we have to compute B star B. And B star B turns into A, which you see here. That results in now having to compute A star A. That turns into A, which you see here. But then we have to work from right to left, right? Going to the far right edge, we have to first compute A star B. That turns into B. Now, in the previous steps, that was already something that occurred earlier. Here it doesn't, so we just have to write this one extra step where it turns into B star B, and then that turns into A, and now we're done. So it was only slightly different, but I just wanted to point that out. And so I'm not going to show the computation for the remaining 4 equations because it's so similar to these. So I'm just going to end the proof of associativity right there. So then what remains is to show that there is an identity element, and hopefully you identified that the element A has the defining property of the identity element, and that's because if you do A times anything, right, you get that thing. So if you do A times A, you get A. That is part of the check that this is an identity element, is that it is, right, when you do A times itself, you get A. And that works forwards and backwards, so to speak. Recall that when you're checking whether something is the identity, you have to compute it on the left and on the right. Well, certainly when you have A star A, they're kind of the same thing. So that's that, right? We see that A acts as the identity with itself, but then we also have to check that A acts as the identity with B. But you look at the table or the list of equations and see that A star B is B, so it acts like the identity for B. Also, B star A is B, so again, it acts like the identity there too. And so in total, it just acts like the identity for everything. So A is the identity for this operation. And lastly, we need to check inverses. That's pretty straightforward also. So we need to check that A has an inverse, but certainly it does because it is its own inverse, right? So to get an inverse of A, we need some element such that when you multiply it with A, you get the identity. Well, we already agreed that A is the identity. So what is the element that when you multiply with A, you get A? Well, it's A, right? So A is its own inverse. So anyway, the inverse of A is A. Next, we need an inverse for B, which again means we need an element that when you multiply with B, you get the identity, which is A. So what is that element? It is B again, right? B is, again, its own inverse because when you do B times B, you get the identity. So there you have it. The inverse of A is A, the inverse of B is B. This checks all the properties for being a group, and so we've proved that this is a group. I just want to end the video with an invitation to leave a comment if you have any questions about anything that is in this video or in any sort of corresponding portion of the textbook. Leave a question, and I may be able to answer it in the comments or make a video to address it.